All right, so this is part 2 of 10.5.
I love that. It's so much fun. I know, it's annoying. Not sure. Yeah, we have. Just gotta
So we're going to talk about arc length and surface area. And so what we're going to do is take what we already figured out about arc length and surface area in parametric equations and just apply that to the parametric form of our polar equations. So we said earlier, when we have parametric equations, our arc length S was integral on whatever our interval was of the square root of dx dt squared plus dy dt squared dt, where x and y are some function of t, where t is our parameter. So what we're going to do is substitute. We're going to make the substitute in polar coordinates. X equals r of theta. R is some function of theta, cosine theta. And y is some function of theta, r of theta, sine theta. And we're just going to substitute these into this expression. These are our parametric equations in polar coordinates. And we know that r varies with theta as well, so we're taking that into account here. We can, I'm not going to do it, but after we make this substitution and we do a lot of algebra, we find in polar coordinates S equals the integral from alpha to beta of the square root of r squared, and let me put theta in there just because we just make it explicit that that's a function of theta, r squared theta plus r prime of theta squared d theta. And usually the way you'll see this written is the more common way is S equals the integral from alpha to beta, just in shorthand, the square root of r squared plus dr d theta squared. And the only conditions, the things we have to be careful with here, we just need to make sure that f has a continuous derivative. We don't want our derivative to give us any problems. And that our curve is only traced once on the interval that we're finding the arc length. So if the curve intersects itself, we have to find the arc length between those points of intersection. We can't go beyond those points of intersection. And if our limits of integration take us around the curve more than once, we have to be aware of that as well. So basically all we've done is plug these in here and simplify. Now I want to, before I do an example, I want to talk about our areas of surface of revolution, and then we'll do an example. So this is our arc length, and just as a reminder, often and when we go further, it will be useful to express arc length as its own quantity. So often we write just generically S equals integral from alpha to beta of ds. So in polar coordinates, ds is this entire expression. That's our little interval, our tiny little piece of arc length. All right, so for a surface of revolution, and this is just, again, we're just using what we already talked about for a surface of revolution using parametric equations, and we're just substituting our expression for x and for y into our arc length integral for polar coordinates. So again, we're saying x equals r cosine theta, y equals r sine theta. Those are our parametric equations, and r is some function of theta. We'll say r is some function of theta. R varies with theta as well. Our surface area, we have two expressions depending on whether we rotate about the polar axis or about pi equals 2. So our surface area, capital S, equals 2 pi, the integral from alpha to beta of f of theta sine theta times our arc length interval, f of theta squared plus f prime of theta squared, d theta. And this is about the polar axis. Polar axis is theta equals 0. So f of theta sine theta is our radius of revolution. Our radius of revolution about the polar axis is the y coordinate. So that's our radius when we revolve that curve about the polar axis. So that's why we have this f of theta sine theta in there. That gives us our radius of revolution. And this is just our piece of arc length that we're revolving around the axis. And then similarly about the axis theta equals pi over 2, we have 2 pi, the integral from alpha to beta of f of theta cosine theta times our arc length expression. And this is about theta equals pi over 2. So again, f of theta cosine theta, that's our x coordinate. That is the radius of revolution as we rotate about the axis theta equals pi over 2. And we have to be sure that our graph has only intersects itself once in our interval of integration. So questions on our expressions, on our formulas. So there's direct extensions of what we've done before. So let me give you a couple of hints when when we're finding these arc lengths. Often we'll have, not often, but occasionally you'll have an expression where we have our equation written in terms of r squared. R squared is some function of theta. If we have this kind of expression, if we want to find dr d theta squared, in this expression, use implicit differentiation. So if we use implicit differentiation on here, we get 2r dr d theta equals f prime of theta. So whatever our expression is for r squared. And then we can simplify this to find dr d theta rather than taking the square root and then integrating. So for example, if we had r squared equals 4 sine theta, if that was our polar equation, we would say 2r dr d theta is 4 cosine theta, and then we can solve for dr d theta much more easily than taking the square root of 4 sine theta and then taking the derivative of that expression with the radical involved. So this simplifies much easier. And when we actually do this process, remember that r, when we divide by r is square root of 4 sine theta, but we're also finding dr d theta squared. So we're trying to find dr d theta squared. So this is much easier than taking the derivative with the radical involved. So that's your hint for finding dr d theta squared when you have something like this. All right, questions on our equations? Okay, let's look at one example of a calculation, and then if we have time, I have another a polar graph where the intersections are not easy to find. Just a slightly different example than the one I talked about the other day. All right. We want to find the perimeter of our favorite cardioid. R equals 2 plus 2 cosine theta. Let me grab a picture of that really quick here. We've talked about this one several times. I think I have it in here. There it is. All right, so let me grab this. So there's our cardioid. We want to find the perimeter. So if we look at this equation, when theta equals 0, our radius is 3. So when theta equals 0, we start out here. When theta equals pi over 2, our radius is 2. So we're going around here. And when theta equals pi, our radius is 0. So we're tracing around here to pi over 2, and when we're at pi, we end up here. So our curve is only traced once on the interval 0 to 2 pi. From pi to 2 pi, we're going to trace the bottom half. So our curve is only traced once, and I'm just going to find the length of the top half and multiply by 2 since the graph is symmetrical. So r prime, we need r prime for our arc length. R prime is minus 2 sine theta. R prime squared is 4 sine squared theta. And r squared is 2 plus 2 cosine theta squared. And when we expand that, we get 4 plus 8 cosine theta plus 4 cosine squared theta. And I'm just going to simplify our expression that goes under the radical for our arc length before I actually start writing out the integral. So we need r squared plus r prime squared. So we get 4 cosine squared theta plus 8 cosine theta plus 4 sine squared theta. And luckily this simplifies a little bit right away. We can combine the 4 cosine squared and the 4 sine squared theta, and we just end up with 4. So when this simplifies, we get 8 plus 8 cosine theta. The 4 from here combines with the 4 here to give me 8. And I'm going to factor out the 8 and get 8 times 1 plus cosine theta. Now, so this is the expression that's going to go under my radical. The square root of 1 plus cosine theta, that's going to be something that's difficult to integrate. But we had a nice formula, a double angle formula that we talked about the other day. 1 plus cosine theta, I'm going to write this over here in my margin, 1 plus cosine theta. This is a good identity to keep in the back of your head, not necessarily memorize, but remember that it's there. 1 plus cosine theta is 2 cosine squared of theta over 2. So when I put this into my integral now I have everything you need to find the arc length. S equals 2 times the integral from 0 to pi of the square root of 8 times 2 cosine squared theta over 2 d theta. And we get 8 times the integral from 0 to pi of the absolute value of cosine theta over 2 d theta. And cosine theta over 2 is positive on 0 to 2 pi, so we don't have to worry about the absolute value. So our surface area, or not surface area, arc length is 8 times 2 sine theta over 2 from 0 to pi, and we end up with 16. 8, yes, this should be in parentheses. 8 times 2. So our arc length is 16 units of our cardioid. This double angle formula for cosine, very, very, very useful when integrating trig functions, and it comes up very frequently. Questions on that one? Yes. Yeah, it's for sine squared would be 1 minus cosine. So let me look at it off the top of my head. I don't remember exactly what it looks like, but there are identities in the front of your book. Cosine, so sine, the double angle formula for sine of 2 theta is 2 sine theta cosine theta. So then you have a u substitution there if you have to do that one. Okay. And there's also a double angle formula for cosine that involves sine squared theta. So if you have sine squared theta, there's a double angle formula that turns it into cosine 2 theta. And that's in the front of your book here. And I think I listed those, was that Friday or Thursday? I put those at the top of the notes, those identities. So usually with arc length and surface area, the kind of challenging parts. One, you have to make sure you get your limits of integration correct. And then two, just because of the form of the integrals can be difficult to work through. So that's usually where the challenge lies. All right, and then I wanted to give you an example. I said the other day we talked about equations, graphing polar equations, where sometimes where we're finding the intersection of two polar curves, that solving simultaneous equations doesn't give you all the solutions, and you can only get them from graphing. And I said usually that problem happens at the pole, which is, in general, that's a pretty accurate statement. But I want to show you an example of one where you get intersections that simultaneous equations don't give you, that aren't at the pole. I just wanted to do a quick example of that, or show you an example of that. So let me go here, I'll close this, and I have it. There. So here's the example I wanted to show you. So what we're talking about is r equals 1 plus sine theta. That's the red graph, the cardioid there. And then in the blue, I had to graph it in 2 points. That's r squared equals 4 sine theta. So the example that I talked about using implicit differentiation, that is the blue curve. When we solve simultaneous equations here, the simultaneous equations only yield the solution theta equals pi over 2. So it only gives us this point of intersection. So we missed 3 points. One of them does happen to be at the pole, but we also have these 2 points down here that our simultaneous equations don't give us. And the only way we can figure out what they are is, or that they even happen, is by looking at this graph. So in this situation, what tools do we have available to us to find those solutions? We're going to graph it in our calculator, right? Hopefully. So we have our calculator. Our calculator would help us out. What tool did we talk about, like the second day of class, that might help us out here? You remember? Newton's method? We're looking at 1 plus sine theta equals the square root of 4 sine theta. So, and I guess we'd have to look at the plus or minus to get the top and the bottom half. So we'd have 1 plus sine theta minus the square root of 4 sine theta equals 0. So we might be able to apply Newton's method to this to find the 0 of that equation. And we have 1 plus sine theta plus square root of 4 sine theta equals 0. Now, applying Newton's method to this doesn't sound very fun because of finding the derivatives and all that kind of thing. But it's a tool that we could use to approximate the zeros. We could get an approximate value for theta and apply Newton's method and do several steps of it and try to get these zeros. So, but my point is that if we were working with these graphs, the only way to find where they intersect is by graphing them. And these we get a couple of intersections that don't happen to be at the pole. So polar equations, polar graphs can be kind of tricky. All right, I just wanted to just show you that as a kind of an interesting extension. Yes.
The ones on the test will yield all the right answers, right?
Yeah, I'm not going to give you anything that's tricky. I just want you to know that they exist, and that you know, interesting, strange things happen sometimes. But yeah, I'm not going to give you anything where you have to apply Newton's method or anything like that to find an intersection.
All right.
It'll be clear either from your simultaneous equations or from looking at the graph that the intersection is, you know, at theta equals 0 and theta equals pi over 2 or something like that.
And so Newton's method with a polar equation would be theta, theta minus at the theta over f prime theta, right?
Uh-huh.
Alright.
I think, yeah, that,
I can't remember Newton's method off the top of my head. Like,
right.
That's the right equation.
Yeah, that sounds like the right thing.
And I'll
So,
double check for sure.
but yeah, it would to calculate all of those and plugging in various values for theta, difficult but doable. All right, so homework. Uh-huh. All right, there you go.